Hello and welcome to today's webinar. It's the second tutorial in our series of Busbar Protection tutorials. And today we will talk about functions, algorithms and settings around Busbar protections. My name is Michaela Mönikes. I think some of you might already know me from our webinars like this or from the Siemens booth where I do guided tours. And that's why I will guide you to today's webinar. And we will start with a short survey, kind of a little warm up to get you a bit busy in our webinar. We've prepared a little Instagauge, a little questionnaire, a survey, and we invite you to either copy the link from the chat or scan the barcode with your mobile, because we want to find out, and now I need the help of the studio, which is the question. I hope that you can already see it, that it's already linked to it. There you go, because we want to know if some of you or how many of you have already participated in our first tutorial around the Busbar Protection series. It had been around Busbar Protection systems and the device selection. So we invite you to copy the code and put it into your browser with a copy and paste operation and then answer the question, or just use your mobile phone and scan the barcode there. I hope that both things will work. And while we invite you to answer the survey, I'm happy to present my first expert here in the studio. I'm really happy that today we have once again Nina Hühn with us. She's definitely an experienced CProtec engineer and a promoter for differential protection. I think she definitely knows more about busbar protection and differential protection systems than I do. And the best thing around that is that Nina will share her knowledge with me and with you. So let's take a look into the agenda. What can you expect from us today? We hope that you will learn about the operation of busbar differential protection algorithms. Then you will learn and hopefully see the advantages of the disconnector image. You will get insights into check zone protection, once again knowledge from Nina, and you hopefully will find the benefits of circuit breaker failure protection. And last but not least, what do you need to know about end fault protection? And you see some breaks in our agenda. And whenever there is a break, we will start a bit, or we'll end a bit early and take your questions to the experts. And how will that work? Please type your questions into the question tool, and I will be your voice at the end of each session, at the end of each part, and ask the experts directly. And I've mentioned experts, so there's at least one more. That's why I gladly welcome Rainer here with me in the studio. Rainer Goblisch is a busbar protection expert, and he's even a member of the IEC and SIGRE groups around busbar protection and busbar requirements. And I think, Rainer, I hope that you out there, the auditorium, is as curious as I am about learning on busbar differential protection algorithms. Rainer, the stage is yours.
Hello, everybody, also from my side. So let's first, before I will start, to explain the details of the busbar differential protection. Have you also participated in tutorial busbar protection session 1, busbar protection systems and device selection? And the answer is 45% answered with yes. So 45% of all participants for today have also participated in our first tutorial. And also, from my point of view, a good news that we have also 55% who started today with the tutorial, and welcome also to these guys. Okay, Thank you very much. The agenda. Thanks. Let's start. First topic, and very big topic for today, will be the biggest one. I try to explain you now the details of the busbar differential protection, the details how they have been realized in all low impedance busbar protection device. So the main idea of our busbar differential protection algorithms have already been implemented in the 7SS52, but of course they have been improved a little bit in the 7SS85. Before I will start, a question also from my side. What is your expected fault clearing time from the fault inception until the trip of the relay? Means when the relay contact of our busbar protection device has been gone to high for an high current busbar fault. So what do you think? What should be, or what is the fault in the absolute fault inception, the fault clearance time? So you have time. We will have a look to the results at the end of my topic for the busbar differential protection. So now we will start. What means low impedance busbar protection? What means differential current measuring principle? Busbar differential protection is simply applying the first Kirchhoff's law. The first Kirchhoff's law means that the sum of all currents, the vectorial sum of all currents, is zero. In case of a busbar, it means we are simply summing up the currents of all feeder, of course also a coupler if we come to couplers, and in a healthy system, this sum must be zero. This has to be done before I get to mention, of course, for each phase separately, for each selective bus zone separately, and also in additional for the check zone. Nina will later, of course, explain in detail what means check zone. It is a stabilized differential current measurement system. We will learn what means the stabilizing. And we call it low impedance busbar protection. That's very important to know, in contradiction to the also quite famous high impedance busbar protection. As here in this principle, the impedance of the relay is low in comparison to the CT circuit. We have a tripping component. The tripping component is a differential current, and the differential current is the absolute value over all currents, over I1, I2, and IN, depending on how many feeders, couplers you have in your system. And we have the stabilization component. That's the stabilization current, sometimes also called the restraint current. It's absolutely the same, which is built and calculated by the absolute value of all currents, the absolute value of I1, the absolute value of I2, and so on. In our device, in all Siemens devices, we both using instantaneous values, momentary samples, and also filtered measurements for our algorithms. Whereas it's important to say the important algorithms are based on momentary samples, on instantaneous values, because they are simply faster. Before I go to the details, I want to explain we are starting every time very simple. And I guess most of you will say, okay, it's quite easy, very simple. But from step to step, you will see it will become a little bit more complicated, really to understand really the problems of the busbar differential protection. First up, the stabilization current. we have, you see here, the black line, that's the calculated stabilization current, the calculated restraint current. But in our algorithm, we are using not directly the calculated stabilization current, this black one. We are using the so-called modified stabilization current. You can see it here. The modified stabilization current is the same like the calculated stabilization current as long as the stabilization current is increasing. But if you see, according to the sinusoidal wave, as soon the calculated stabilization current is decreasing, the modified stabilization current is decreasing only a little bit in a linearized wave form. And the reason is also to have a high stabilization current during the zero crossing of the sinusoidal wave. And every time if we are saying we are looking to the characteristics, and you could see we have on the y-axis the differential current, and we have on the x-axis not the calculated stabilization current, we have the modified stabilization current. And the device will trip. We say there will be in the stabilizing area if we are below the characteristics, and the device will trip if we are above the characteristics. And important, on the x-axis, we have every time to think about the modified stabilization current and not the calculated stabilization current. We will see later in the examples how important this is. Let's, for our imagination, how to think what's behind all these characteristics, let's have a look to some examples. We start with a small example. We have a simple busbar. We have only two feeders. We have one in-feed and we have one outgoing feeder. And it's very important to understand, we will see more examples in this way with only two feeders, that two feeders is every time the worst case scenario, especially if we come to seed saturation. So seed example with only two feeders is the worst case example, and all others with 3, 4, 5 feeders are not as so important and not so difficult like an example with two feeders. Okay, we have here the characteristics on the left side. We have an operation point, means we have in the ideal system, we have 0 differential current. Sorry. Oh, yeah, sorry, I'm struggling. And then an external fault will happen. And what happens for in case of an external fault within an ideal system, the differential current will remain 0. But the stabilization current, which is the sum of the absolute value of these two feeders, will increase. And you will see, let me see, so that's the normal operation. Then we have the external fault. That means stabilization current will increase a lot. Okay. Next example, also an ideal example. Let's look how an ideal bus fault will look like. We start once again with a small example with a strong infeed and an thanks with a strong infeed and an outgoing feeder. And now we are still have the operation conditional, means we have a stabilization current in the area of the operational current flowing. And now we have an ideal internal fault. That means that the in-feed current, I1, the differential current is the same as the in-feed current, and the stabilization current is also the same. Means we have a fault on the fault line, means with the stabilization factor K is 1, we have really an ideal fault. CT errors. What exactly means CT errors? So CT errors is mainly the inaccuracy of the whole system, mainly the inaccuracy of the primary current transformer, the inaccuracy of the secondary current transformer in the device, of the whole measurement acquisition system in the device, and so on and so on. And we have the stabilization current, which is also the same. So here we have, so typically, a small differential current caused by the CT errors, caused by the inaccuracy of the whole system. And this is, of course, also proportional to the stabilization current. Means if we have in parallel and external faults, means the stabilization current is increasing, and then typically also the inaccuracy will also increase. So means this so typically the flow of the CT errors of the differential current caused by the inaccuracy. CT trouble. Very important slide now. What means CT trouble? CT trouble means mainly we have lost one CT, lost a complete CT for all phases, or lost CT of one feeder only for one phase. It doesn't matter because enough differential current in one phase is enough to clear, to trip the whole system. And here, this means CT trouble, the loss of one CT will cause the differential current of the load current of the CT we lost. So we have here CT trouble, and now we come to one of our most important settings. So you see in our characteristics, we have here the minimum differential current. And the most important rule, the most important setting rule is that the minimum differential current threshold, you see it here in the characteristic, should be higher than the load current of the feeder or of the coupler with the highest load current. The reason behind is that the philosophy of busbar protection is that with one single trouble, with one single fault, it should not happen that you will lose a complete busbar by fault. So it should every time two criteria to prevent an unwanted trip of a busbar. And therefore, once again, this minimum differential current threshold should be higher than the load current of all your feeders you have in your system. So if you lose the CT of the feeder with the highest load current, you will not risk an unwanted trip. Of course, sometimes I forgot to mention this, the minimum differential current should be also lower than the minimum short circuit current. That's also very important. And we will see it when we come to the sensitive characteristic, that sometimes we have a problem in a really zero resistance grounded system. Normally this is no problem. If we have a resistive grounded system, this may have a problem. We will come to it later. Okay, let's stay on this very important slide. But we say this minimum differential current threshold should be higher than the load current. But what happens if in parallel we have the CT trouble, we have during maintenance activity or anything else, we have lost the CD, everything is fine. We will have a differential current, but we will not trip because the minimum differential current threshold is higher. But if then in parallel we have an external fault, we would trip nevertheless, because then of course this CD which have been lost would have bring more CDs which is missing, and we would pass the characteristic and we would be in the tripping error. And therefore we have one further very important setting. That's the threshold of the differential current supervision. And this threshold of the differential current supervision should be lower than the lowest load current of all feeders. Because if you lose one CD, you should be for sure above the differential current threshold. And via this differential current threshold, you can block your busbar protection systems in order not to risk a wrong trip of the busbar, because then in parallel you will have an external fault. Okay, very important. Also, the next thing is very important. Now we come to a very simple explanation of the desaturation. You will see that's a quite simple model. It will become a little bit more realistic in the next slides. We will start at operation point A. We call it the pre-fault operation point. Means the system is fine. We have a certain stabilization current. We have no differential current at all. And then we have an external fault, which increases the current a lot. And then the stabilization current will increase and increase. And at operation point B, it will come to a CD saturation. And you know, CD saturation means not only the primary CD is not able to follow the increase of the current, it will go to zero. The current will go to zero. This means we will not have only differential current. We will have differential current, and both the stabilization current will decrease. So that's what happened after point B. And at point B, we will come to C, and at C, maybe the CD saturation will stop, because we will go to the other direction of the sinusoidal wave. And then we will have a differential current in case of an external fault, which is a function of the CD saturation. And we have the stabilization current, which is the absolute value of all currents. But as already mentioned, for example, current I2 will be the current from which will saturate. This component will also decrease. And then whether we will trip or not depends on our used stabilization factor. This is a very simple model with a stabilization factor of K is 0.5, and trip may happen. It's not absolutely sure, but we have at least the risk of a wrong tripping. But with a stabilization factor of K is 0.65, we would be in the stabilized area and everything should be fine. So, time for first sum up. We have, for our busbar differential protection, we have very low settings. We have two settings which are maintaining and cover CT errors, cover CT trouble, and also cover CT saturation. We have the minimum differential current threshold. Also think about the minimum differential current threshold of the differential current supervision, but it's not so for the busbar differential protection else, it's an additional supervision. And we have the K factor for the stabilization. Let's have some small examples. Once again, worst case. We have here a busbar example with a very strong infeed with a big CD, 2500 amps to 1, which we here call it the current I1. And we have a small outgoing feeder, which we call now the I2. And we have an external fault. And let's see, and you will see, next slide, that here we will see the current, of course, in a normalized way. So let's say here we have the 2500 amps is normalized value 1 here in this example. And we see this blue dotted line will not saturate, but I2 will saturate, that's its violet color, will saturate after about 60 degrees, which means so round about at 3 milliseconds in the 50 Hertz systems. Let's have a look according to this currents, how the differential current and the stabilization current will look like. So we will have the differential current. Here's this red line. You see before, if we start on the left side or at 0 degree, I2 has not saturated. So at the very beginning, we have 0 differential current. You see it here on the left side, the red line, the differential current is 0. But when I2 saturates, suddenly the differential current jumps, and it will be, because I2 is absolutely 0, the differential current will be the same as I1. So it's similar to I1. The stabilization current, this you will see the dark green line, the calculated stabilization current. You will see it, it's I1 plus I2. And you will see here, the calculated stabilization current will decrease as soon the CD saturations of I2 will start. And that's the reason also we are using, as already said, for our tripping criteria, not the calculated stabilization current, we are using the modified stabilization current. So here in this picture you see very good, and maybe also the reason why we are using the modified stabilization current and not the calculated stabilization current. So the stabilization factor with K is 1. And so here's the tripping criteria would be that the differential current should be above the modified stabilization current, but with stabilization factor K is 1. Of course, we have absolutely no risk of any tripping, but unfortunately, with a stabilization factor of K is 1, we would also not trip in case of an internal fault. So a stabilization factor of K equal to 1 makes no sense. So let's work with more proper stabilization factors. Here, we see here with a stabilization factor of K is 0.5, it could be critical. So at least 2 times, the differential current is above the modified stabilization factor. This means a risk may happen. But with a stabilization factor here in this example, K is 0.7. We see everything is fine. We would not risk any trip. I have explained this very important criteria that the minimum differential current threshold should be higher than the load current of the feeder with the highest load current. In a resistive grounded network, typically this criteria cannot fulfilled because of the resistive grounding, and phase to ground fault would lead to quite low fault currents, which are typically not above the load current. And in this case, in order not to risk a wrong tripping in case of a fault, we have to use the sensitive characteristic. So the sensitive characteristic should mainly used in resistive grounded networks. It will also not work because during the last week, I have some discussion whether this can also be used for isolated systems, because also in isolated systems, we have a current due to the capacity of the cables in case of a fault, but it cannot be predicted. So really the resistive, the earth fault characteristic should be used only for resistive grounded networks, not for completely isolated networks. In this system, we have very low earth fault currents. So the differential current is less than the highest load current, what I have already said. We can work with this characteristic, but this characteristic should not be activated every time. So the sensitive characteristic should be activated by a second criteria, which is the indicator of an fault, of an phase to earth fault. And typically we are using here the displacement voltage. So we are measuring the displacement voltage. If we are detecting a displacement voltage, we will activate the sensitive characteristics, and then everything should be fine, and we are really also on the safe side. Okay. I hope the sensitive characteristic is clear. Otherwise, of course, you have the possibility to ask questions. Let's come to the details of the algorithms. We have 3 algorithms working in our device. And the criteria for the selection are the current magnitude, is the slope of the stabilization current, I will explain later, and it's also the fault location. I will also explain how we will detect the fault location. We have the very fast 1 out of 1 algorithm, which is invented for very high fault current. Very high fault currents where the desaturation may happen later. And here, the typical tripping time is 7 milliseconds at the trip relay. These 7 milliseconds are for the centralized busbar protection and with the type F, the fast output relays of the Protect 5. But here really the 7 milliseconds are really from fault inceptions until the binary output of the device has been activated. We have the 2 out of 2 algorithm, which is for medium and low fault currents. And very important, the 2 out of algorithm is also responsible for evolving faults. And here's the typical tripping time with the same requirements I have explained before, are 17 milliseconds at the trip relay contact. And fast but not least, for very special fault conditions, for really very low fault levels, a little bit above the differential current threshold, and with high DC offset, with high DC components. And here, last but not least, quite slow, 27 milliseconds, centralized busbar protection, and so on. But we are speaking here really for quite low fault currents. So typically, you will not have the risk when the filter algorithm has to apply. We will not have the risk of burning any contacts anywhere because it will clear only very low fault currents. Very high current faults will be typically tripped every time with a 1 out of 1 algorithm. The slope of the stabilization current means here really a jump of the stabilization current. We will come to later. So really the change of the stabilization current per time. So typically, as the cycle time of the busbar protection is 1 milliseconds, means really the slope, this change of the stabilization current, the jump within 1 millisecond. The 1 out of 1 algorithm, we call it also the sub-cycle tripping. The characteristics is every time triggered and must be triggered by a jump of the stabilization current. For busbar faults, for internal faults, the tripping condition must last for only 1 sample. And this is really our most important algorithm, guarantees a fast trip of busbar faults. And if you use high-speed relays, our electronical high-speed relays, this 1 out of 1 algorithm can trip really a busbar fault within the complete time with 3 milliseconds. Very important for external faults, for high current external faults, where also a CD saturation may happen later. And here the 1 out of 1 algorithm is not very safe against the desaturation. The 1 out of 1 algorithm will be blocked. Okay. And for external faults, the CD must stay without saturation also for only at least 2 samples. And we will see it in the example. The 1 out of 1 algorithm takes advantage from the saturation-free time at the beginning of a period, at the beginning of a short circuit. So 2 out of 2 algorithm and Fourier algorithm. Here, the tripping condition must be fulfilled for at least 2 successive half cycles. It provides a stability at heavy saturation and also for heavy transient DC components. Very important, that's cause for the 2 out of 2 algorithm, not for the Fourier filter algorithm, that the 2 out of 2 algorithm has to trip also evolving fault. That means evolving fault, a fault which started externally and after 10, 20, 30, 50 milliseconds or 100 milliseconds went from an external fault to an internal fault. That's an evolving fault. And also for high resistance busbar faults. So now we are just before my favorite slide. Let's sum up before I will come to explain really the coordination of the algorithms. We have 3 criteria. We have the criteria A, which means that the differential current must be higher than the minimum differential current threshold. You see it here on the characteristics. That's this criteria A. We have criteria B. That means that the differential current must be higher than the modified stabilization current, not the calculated, the modified stabilization current, multiplied with the stabilization factor. And we have criteria C, which you can't see directly here at the characteristics, which means we have a jump of the stabilization current. It's an internal value that are detected from 1 millisecond to the next millisecond. We have a very high jump of the stabilization current, and this jump of the stabilization current, we say that's criteria C. The coordination of the algorithm. So just listen to my words. Afterwards, you will see if you later in some months or days want to follow, you will see also the explanation on the right side of the slides. But now I try to explain you, and so just listen to my words. You have here on the right side of this diagram, you have the trip. That means you have the trip. It will be the trip of one phase of one selective zone, or it can be also the criteria of one phase of the check zone. You have a trip, and you have 3 inputs. You have one input from the 1/1 algorithm, that's red bars. You have the input of the 2/2 algorithm, that's the green bars. And you have the input of the filter algorithm, which is the blue bars. And you can see each algorithm completely independent is sufficient to trip a bus bar, a bus zone, or the check zone. Let's start now to the left side. We have criteria C, means we have a jump of the stabilization. Thank you very much, Nina. That's a very good animation. We have here the jump of the stabilization current. We have criteria C fulfilled. And here, if I have really a training with where the participants online, I ask every time, okay, we have the jump of the stabilization current. Is it now an external fault or is it an internal fault? And some guys answering it's an external fault. Some guys answer it's an internal fault. And some guys are right, as hopefully also you. We have no idea. A jump of the stabilization current criteria C could be both. A jump of the stabilization current will happen both in case of an external fault and also in case of an internal fault. But let's have at the very same moment, at the same millisecond, if we have a jump of the stabilization current, and at the very same moment, are we in the tripping area or not? Is criteria A and B fulfilled? Here, that's this here, Nina, this end getter, with this, where this criteria A and B comes in. If we have in parallel together at the very same moment a jump of the stabilization current, and we are in the tripping area, then we can be sure it's an high current internal fault. And we will immediately trip, such as red bars, we will immediately trip according to 1/1 algorithm. If we have this jump of the stabilization current, and in the very same moment, we are not in the tripping area, means the differential current is below the minimum differential current threshold, or it's below the differential current multiplied with the stabilization factor. Exactly. I thought there's a wrong here, something in the slides. Then we are sure it must be an external fault. So jump of the stabilization current in the very same moment, we are not in the tripping area. Then it must be an external fault. And very important, now we have to block immediately the 1/1 algorithm and also the filter algorithm. Because maybe 1 or 2 milliseconds later, a CD saturation may happen. So if we have this jump and we have at the very same moment no differential current, we will block for 150 milliseconds both the 1/1 algorithm and the filter algorithm. Okay, but let's go through the other possibilities. We have no jump. We are simply in the tripping area. So the differential current is higher than the minimum differential current threshold, and the differential current is higher than the stabilization current multiplied with the stabilization factor. That means we are in the tripping area. And 1 threshold exceeding is enough. We will start the 2/2 logic here in this green way. So that means we will not immediately trip with the 2/2 algorithm. We will start a 2/2 logic, which will come in the next slide. And also in parallel, if not blocked, we have our filtered algorithm, which has also its own logic and can separately trip the busbar. Okay. And here, that's hopefully the explanation I have given to you now, if you want to read it later by your own. Two out of two algorithm. I have already explained one threshold exceeding is enough, to start the 2 out of 2 algorithm. Of course, but that's the same for the 1 out of 1 algorithm, but as we have here in separate slide, we will start the 2 out of 2 algorithm only if the differential current supervision has not picked up and if any measured value supervision has been picked up. But I think that's a separate topic we will explain. Supervision, Nina? Third or fourth tutorial, something else, at least later. Okay, one threshold exceeding is enough, and then the algorithm will start at that time. At that time of 8 milliseconds in a 50 Hz system, and for 6 milliseconds in a 60 Hz system. Why is this 8 and 6? This datetime must be enough to be sure in the second half wave of the sinusoidal wave. So the 2 out of 2 algorithm has to be ensure that we will trip only if we are in the tripping area for 2 succeeding half waves. So one threshold exceeding, we start at that time, and then after 8 milliseconds for a 50 Hz system, we are starting a 60 millisecond measurement window. It's only 5 milliseconds for a 60 Hz system. And within this window, we must fulfill 4 threshold exceedings. If this is fine, we can say, okay, we are in the tripping area for 2 succeeding half waves. We will trip according to the 2 out of 2 algorithm. If not, we have to reset this flip-flop. And why is the flip-flop? You would memorize whether this criteria is really fulfilled in 2 succeeding half cycles. So we will reset it. So with the next threshold exceeding, we will start at the very beginning. 1 threshold exceeding is enough, that time, and really only for 2 succeeding half cycles. And this will be ensured via this flip-flop, which has been set after the first threshold exceeding. It will be reset if in the next measurement window we are not fulfilling the criteria. Okay. Let's come to some examples with the things we have learned now. Let's come to an external fault without any CT saturation. We see here, it's quite boring, I guess. We see here the differential current is 0 because it's an ideal external fault. And we see the calculated stabilization factor, which is going to 0. And very important, only just to once again see you really on diagrams, on figures, what I have tried to explain to you. You see the modified stabilization current multiplied with the stabilization factor. That's this brown color here. And if you see the modified stabilization current multiplied with the stabilization factor, and in comparison, the differential current, you can directly say if the differential current is above the modified stabilization current multiplied with the stabilization factor, you are in the tripping area or not. But this is quite easy example. We have no differential current at all, so nothing could happen. Bus fault, a little bit more interesting. We have a quite bus fault. We have here the differential current, which is also going to 0. And here we see once again, here now in white color, the modified stabilization current with multiplied with the stabilization factor. And now, once again, maybe you can answer by yourself my questions. Will here the 1 out of 1 algorithm immediately trip? You can think a little bit by yourself and answer. And the correct answer is you can't answer these questions because you do not know our internal criteria. You don't see any, how to say, on the y-axis, how big is the nominal current or anything else. So simply you can't answer in this case whether we will trip according to 1 out of 1 algorithm or not. Let's assume it seems like a not too big internal fault. Let's assume we will not trip according to 1 out of 1 algorithm. We will trip according to 2 out of 2 algorithm. So for the 2 out of 2 algorithm, we have learned 1 threshold exceeding is enough. We have this measurement window after 8 milliseconds, and then we have a measuring window of 6 milliseconds once again. And within this measurement window, we have to reach 4 threshold exceedings. Let's have a look. So 4 threshold exceedings, okay. We will do it here according to 2 out of 2 algorithm. Now, it become a little bit now to the end. Our examples get more and more complicated. You remember this example with a strong in-feed, 2500 amps to 1, and the small outgoing feeder with a small CT, 400 amps to 1 amps. We have an external fault with CT saturation after 60 degrees, after around about 3 milliseconds. We have the I1, the in-feed, that's white. Looks a little bit like blue, but should be white, this big current. And we have a heavy DC displacement. We have a DC offset. You could see this in-feed current. We have a strong DC offset in the opposite direction. And we have the outgoing feeder, that's this brown color, which will saturate after around about 3 milliseconds. And now let's look again with this more realistic example with this DC offset, how the differential current, how the modified stabilization current looks like. Here we have now in this diagram, the red color, that's the differential current. The white line is the stabilization current multiplied with the stabilization factor. And the most important thing for us is this brown line, which is a modified stabilization factor multiplied with the modified stabilization current, multiplied with the stabilization factor. And very important are in our algorithm, as already stated, as the saturation free time. Here you could see here during my animation by this, it was blue or green or rectangle, and now animated also by Nina with his mouse. Thank you very much. You could see we have here this differential for the first 3 milliseconds. The differential current is 0, and you see it here, the stabilization current. You see a big jump of the stabilization current. And now, if you remember back to the coordination of our algorithms, what happens? We have fulfilled criteria C. We have this big jump, this high jump of the stabilization current. We do not know, is it an internal or external fault? But if we looking at the very same moment, whether we are in the tripping area, whether criteria A and B fulfilled or not, we can say now it's an external fault because we have the jump of the stabilization current, but we are not in the tripping area as the differential current is 0. So what we will do, we will immediately block the 1 out of 1 algorithm and also the filter algorithm. So these are this very important first 3 milliseconds, the saturation-free time after unfold. Here, that's the next phase. Now we have the differential current, which is very high. And here, first time you see it, maybe Nina, once again, where the differential current, the first time is above, is in the tripping area. We have learned here, now we have one threshold exceeding, which is enough to start the 2 out of 2 algorithm. The 1 out of 1 algorithm has been blocked, but we will start here the 2 out of 2 algorithm. Here's the first time. So, and we see, now we will start the 2 out of 2 algorithm, but we have learned the 2 out of 2 algorithm, we have to be in the tripping area for 2 succeeding half cycles. The 1 out of 1 algorithm is blocked, but the 2 out of 2 algorithm has to be looked whether we are in the tripping area for 2 succeeding half cycles. So, first 2 periods, areas with differential current is above the modified stabilization current, but we have no trip by the 1 out of 1 algorithm. The 2 out of 2 algorithm will not trip. You can see here that's the period 1, and the second period will be this blue one, but here, which would be the measurement window for the second half-wave of the 2 out of 2 algorithm. But here, during this time, we are not in the tripping area. Then, once again, we would start the 2 out of 2 algorithm by period 3, once again, but in period 4, we are once again not in the tripping area. So we would have no trip here in this case, whereas we are 2 times in the tripping area. So it's time to have a little bit water. What is missing? I hope you have now understand mainly the coordination, 1 out of 1 algorithm, blocking 2 out of 2 algorithm. What we have not so talked much about is the filter algorithm. So let's have here this small example of a busbar fault with a quite low current with the desaturation and a very strong DC displacement. Here we have this trip by 1 out of 1 will not happen because here you see on the y-axis the nominal current. The nominal current is in the maximum only 2, and this will for sure not trigger a 1 out of 1 algorithm. So the 1 out of 1 algorithm cannot trip, and the 2 out of 2 algorithm has also no chance. Here's a 1 out of 1 algorithm because we have, you could see here this little jump of the differential current, but which is still above the modified stabilization current. So for the 1 out of 1 algorithm, the fault current is simply not high enough, and for the 2 out of 2 algorithm, we are not in the tripping area for the second half wave. So only when the DC component is declined, so that's roundabout here in this example after 100 milliseconds, then the 2 out of 2 algorithm can be applied and will trip. But okay, also for a quite low fault current, a tripping time of more than 100 milliseconds is not so fine. And so far, I guess it was 25 years ago with the first RTTS test of the Busbar Protection. And then we invented additionally for this very special case, the filter algorithm. So let's have a little bit of look to the root cause of the problem. We have here the differential current, which you can simulate, for example, just to infeed one current into a bus zone, and then you will have a differential current. And we have the differential current threshold. And then if you add a quite high, you are only a little bit above the threshold, and you have a DC component. And then you will see that for the positive direction, it's no problem to overreach the minimum differential current threshold. But in the opposite direction, due to the DC offset, you will not reach the minimum differential current threshold. And that's simply the problem of the example before. Because you are a little bit above the minimum differential current threshold, you have a DC offset, and the 2 out of 2 algorithm is looking to beat the Turing error for the 2 succeeding half waves, and then you have a problem. And what will be the solution? The solution will be a filtered algorithm which will eliminate the DC offset. I guess last slide. Here is a small example to show you a little bit the principle of the DC offset. We have in this first, please make it big, Gat. I need this. Okay. Here the characteristic in the middle, that's K1, that's the measurement point. We once again only injecting in a bus zone only one current. And we have a strong DC offset here in the negative direction of the y-axis. And you see the differential current, which is the characteristics at the top. You see a very big differential current when the sinusoidal is really completely in the negative direction. And you have a very small differential current for the other half wave. And then, once again, you will have the problem. You will only be above the minimum differential current threshold for one direction of the sinusoidal wave. And what we are doing now, we are applying, you can see it here, the sinus-cosinus filters with some filter coefficients. But the disadvantage is, of course, you have a measurement window of these filters, and this measurement windows is coming from the past to the future. And you need a little bit time when all the sampled measured values which have been passed through the filters are completely in the measurement window. So this needs around typically 20 milliseconds, one cycle. But if the fault inception is completely in the measurement window, you will have a stable differential current, you will have a stable stabilization current, and you can make a stable decision whether to trip or not. It needs a little bit time, but then for sure. So we will have typical tripping time of 27 milliseconds. Sounds quite long compared to the 7 milliseconds of the 1 out of 1, but much better than the 100 milliseconds for the 2 out of 2 algorithm in this case. Okay. It was a long time. I promise it was the biggest part for today. Now it becomes hopefully a little bit not so complex and much. And now we come to your answers. Let me go one step. What is your expected fault clearing time from fault injection and trip the signal of the device for a high current bus fault? So the expected time, 1 milliseconds. It's 10%, 7 milliseconds. Oh, thanks. 7 milliseconds, 28. 37% are expecting 50 milliseconds. And okay, 11%, 30. And even 14% of you will still or expecting a tripping time of 50 milliseconds. Okay, so thank you very much. You have learned. If you have really a high current internal fault, our centralized busbar protection will trip with 7 milliseconds, our distributed also with 9. So we will fulfill, and 15 milliseconds is no problem in any case. So thank you very much. And now, as said, I'm also now glad that the next part will take Nina. I know this maybe will be the hardest theoretical part of our whole tutorial series, and I would ask you, how did you appreciate the speed of the last part, what I have during the last hour, learn how busbar differential protection algorithms operate and understand the relevant settings. So, and I guess we will we have a look before the break, I guess. Okay, thank you very much, and welcome, Nina.
Okay, yeah, thank you, Rainer, and hello to everyone out there also from my side. In the next roundabout 15 minutes, I want to talk about the importance of the disconnector image. For the disconnector image, the position of the disconnectors is used to assign a feeder to a busbar. This is necessary to achieve selectivity in the event of a fault, which means to disconnect only those feeders that are connected to the busbar on which the fault occurred. Okay, but before we go too deep into the subject, I would like to talk about the acquisition of the disconnector position. The picture on the left side of the slide shows a double busbar with two disconnectors, one circuit breaker, and one current transformer. For each switching device, two auxiliary contacts are connected to the Cyprotec 5 device, a normally open contact and a normally closed contact. I will explain later what that means. The principle for the interpretation of the input signals is that not open means closed. The closed state is the safe state. If the disconnector is closed, the feeder is assigned to the busbar and part of the protected zone. If a disconnector is incorrectly recognized as open, this could lead to an underfunction in the event of a fault, and yet this must be avoided. The connection of both the normally closed and the normally open contact is not mandatory but recommended. With both contacts, the supervision of the running time and the binary input and supply voltage supervision is possible. A disconnector or circuit breaker provides two signals for the limit positions of the switch, the normally open contact and the normally closed contact. The normally open contact is open when it is in a de-energized state. So the state 0, which means no voltage, corresponds to the state switch open. A 1 or high signal corresponds to the state switch closed. In the information routing in Dixie, the normally open contact must be connected with a closed high to the position information of the switch, because the high state means closed. With the normally closed contact, it is the other way around. It is closed when it is in a de-energized state. So the state 0 corresponds to the state switch closed. A 1 or high signal corresponds to the state switch open. The normally closed contact must be connected with an open high to the position information of the switch in the Dixie information routing. On the last slide, I explained that the safe state is the closed state for a disconnector, because then it is assigned to a busbar and part of the protected zone. When you only connect one position signal to the Cyprotec device, use the normally closed signal. Because even when there are problems, in example with the power supply, the de-energized state is the closed and therefore the safe state. Preferably, you connect the 3 auxiliary contacts of the 3 phases in series. This is shown on the picture on the right side of the slide. This ensures that the disconnector is treated as open only if all 3 poles are opened. In all other cases, the disconnector is processed as closed. The first diagram on the right side of the slide shows the status of the physical switch. It changes from open to closing to closed and back to opening and open. In the red marked area, arcing is possible. The feedback of the normally closed and normally open contact are the final position of the switch. The normally closed contact changes its status from open to closed as soon as the disconnector starts closing, and it stays closed until the open position is reached. The normally open contact changes its status from open to closed when the disconnector is completely closed, and it changes back to open as soon as the disconnector starts closing. In the opening and closing process, both signals are 0. The running time of closing and opening can be supervised by measuring the time where both signals are 0. That means the normally closed contact is already closed, but the normally open contact is not yet open. For the running time, a maximum time span can be defined in the settings. If this time span is exceeded and something is wrong with the disconnector, you can decide by setting if this should block the protection or if it should just be reported. When the normally closed contact signals the circuit breaker is closed, the current is assigned to the busbar differential protection. This is meant with this green diagram. And yet this underlines the importance of the normally closed contact. The table on this slide shows the input of the contacts, the resulting status of the disconnector, and the reaction of the protection device. When the normally open contact is 0 and the normally closed contact is 1, the disconnector is clearly in an open state. When the normally closed contact and the normally open contact are 0, for one of the disconnectors in a bay, the state is closing or opening. The current is assigned to the busbar protection and the supervision timer is started. The normally open contact is 1 and the normally closed contact is 0. The disconnector is closed. If both contacts are high, something seems to be disturbed and a supervision timer is started as well. If there is a supply voltage failure, all position inputs of one bay have the status 0. In this case, it can be decided by setting if the last known position should be assumed or if the disconnector status should be closed. The benefits of the disconnector treatment are that there is no need of adjusted contacts and the busbar protection is active even during the disconnector transition. Okay, let's come to the bigger picture. Knowing the disconnector position, a feeder current can be clearly assigned to a busbar. In this example, there's a double busbar with 4 feeders and 1 coupler. In the first 2 feeders, the right disconnector is open, the left one is closed. The feeder current is assigned to the measuring system of busbar B. For the other 2 feeders, it's the other way around. These are connected to busbar A. The CTs are colored in red and blue, dependent on the assignment to the busbar. The coupler in this example has only 1 CT, and this CT is assigned to both measuring systems. With at least 1 CT and a circuit breaker in the coupler, you've got 2 independent measuring systems, and a selective tripping is possible. In case of a fault on busbar B, the red one, only feeder 1 and 2 and the circuit breaker in the coupler must be tripped. For a fault on busbar A, it is feeder 3 and 4 in this coupler circuit breaker. In case of a temporary bus coupling by the disconnectors in one feeder, a selective tripping is no longer possible. All feeders of the coupled busbar are assigned to one preferred measuring systems. The bus zone with the lower instance number according to the engineering is preferred. The currents in the bus coupler are ignored in case of a busbar shunt by the disconnectors. Okay, I think we've all earned our first break, but before the break, we still have time for first questions if there are already any. Martina, Rainer, will you join me on stage?
Yes, we will. Thank you, Nina. And there are a lot of questions already in the questions tool, and I'm going to present at least some of them to you. Let's see, do we have, I need then some information from the regie, how long time we will have for the questions, but nevertheless, we'll start with them. And the first one is one that I will answer because NCI wants to know, or thanks for the webinars, helpful content in there, and mentions that they take time during working hours. That's true. That's our working hours, and we hope that it's useful for your work too. But if you want to see them at the later stage or take part in the webinars at a later point of time, that's no problem. We record the session, you will get access to the presentation, and whenever the time suits you, you can access the recording. I think the link will be sent out within the next days at the latest to access the recording. And so now we take the first question to you.
Would
Yeah.
we start with the answer of my questions? How they appreciated the speed?
Oh, yes, that's a good idea to come back to the survey. And 75%, so that's a majority, already tells us fine, it was appropriate. You're not too slow, definitely. Nobody was bored, but for some of you, and I think I'm one of those, it was a bit too fast and sometimes they got lost. I hope we got you back on time. Yeah, I mean, that's why we have these expert sessions, right? So I hope that for you, that where it was a bit too fast, I mean, just take the recording and figure it out again. And I think it helped that we put in the mouse movement and show where we were on the slide. And I hope it even was or improved throughout. And if you still have questions, I mean, that's why we are here. That's why we have the experts right here. So now my question for you from JW. Is the 7SS85 suitable for distribution substations where the earth fault current is restricted to 300 to 900 amps by neutral earthing resistors or neutral compensators? So that's really technical questions of this, if it's suitable, the 7SS85.
So that sounds like a compensated network. And I guess that's exactly what I have mentioned, that here's this fault, this earth current comes mainly from the capacity of the cables. And maybe I would need exactly a drawing, but tentatively I would say no.
Okay, so in this case might be a direct contact more helpful. And I think the same is true for the next questions I see there from KSM. KSM is configuring the 7SS85, but can't initialize the relay. So how can I handle it? Seems like we have some technical problems there. Maybe the hotline, right? We cannot send it from here, from the studio. I hope that our hotline will be able to help there. So let's go for the next one. And I think it's in that double because NAABB placed the question a second time and there it's complete. And that's a long one. So please kindly requesting to you. I don't know how to clarify if we are clarifying if we are using metal oxide varistor or non-linear resistor in high impedance current differential busbar protection to suppress the voltage when the fault current happened due to fault at the same time in low impedance current differential busbar protection. We are using two slopes, it is slope 1 and slope 2, whichever low breaker point and high breaker point to suppress the voltage. But here we don't have MOV in low impedance busbar current differential protection. Then how is it possible in low impedance busbar differential protection to suppress the voltage based on just two slopes? Can you clarify that? That's a long one.
Mhm.
And do my experts understand it? I didn't understand a word. I read it, but I'm no specialist at all. Can we take that here in the studio, or will we take that offline? So better reading. And the good thing about these questions...
I will try to read it really on my own, very slowly, and I try to understand. But I guess there will be a separate meeting maybe to explain.
Probably. And that's what I like to tell you. You will not get only access to the recording and to the slides, but we will also send out, I think not in the next hours, but within the next days, the questions and the answers from the experts. So yes, we will somehow answer that. And if you're not able to answer the question as it's told here, we will find a way to contact you. So I think that the next one is a question regarding one of your first slides, because it came in rather early. So IDEF and ISTEP are calculated from filtered values from DFT/cosine filter or from instantaneous values.
I hope it will have been answered during the next slides, because we are using both instantaneous values for the algorithms. That's the algorithms I explained here, really where the differential current is 0, and the filtered algorithm here, values which come from this filters, this cosine and DFT filters, both are used. Both filters and directly instantaneous values are used. There are different algorithms. So answer, we are using both.
Perfect, thank you. Yeah, it could be that some of the questions had already been answered, but nevertheless, we see that you take part of the presentation. So thanks for all the questions. So TT wants to know, with regards to bias settings, IDEF, for tripping characteristics for CT trouble, how do we arrive at this IDEF value?
How do we arrive? It's not clear how do we arrive at this IDEF value. Is it clear to you?
Not completely. Maybe we can mention here that in case of an external fault or internal fault, of course, the currents are high enough to reach the tripping area, and you don't have to worry that the setting is too unsensitive here.
Maybe this question means in this direction how to evaluate which minimum differential current threshold should be set. But here I think you know the substation, the customer has to know which feeder do I have and what are the separate nominal currents of the separate feeders. So typically this has to know the customers, this has to know really the owner of the substation, what are the nominal currents, what is the operational current of the whole substation, and what are the operational current of each separate feeder. So, and then you have to look for I go into a direction, hopefully I am right with this answer, and then you have a feeder, you have one feeder with nominal current, this may be the infeed of, let's say, 1200 amps, and you have some feeders with a nominal operational current of 800, 700, and then, as I have said, the operational current of the feeder with the highest value should be, the differential current should be higher than the operational current of the feeder with the highest current. So let's say here in this example, we have the biggest feeder with the highest nominal operational current is 1200 amps. And then you should select at least a minimum differential current of 1400 amps.
Okay, thanks. So next question is from AA, who wants to know, for double busbar, double breaker systems, is it recommended to use one central unit or 2 units, one for each bus bar for the same voltage level?
It is possible with one central unit. You want to add something?
No, you can use both, but if you have to look for an economical solution, it's absolutely fine, and I would recommend, as Nina has said, with one central unit for sure.
Okay, I think then we talk about the saturation, because the next question from MP wants to know, does the SIP5, so the CPROTEC 5 device, does it not monitor the condition of the current in the CT loop? And thus, would it not be able to detect the CT trouble in this case? A lot of nods. So does the SIP5 monitor the condition of the current in the CT loop? And would it be able to detect the CT trouble?
I guess this goes a little bit to the standard CPROTEC 5 CT trouble supervision. But we have disabled this for the busbar differential protection, because the standard CT supervision, I guess this is meant with the CT loop and CT trouble, will pick up only after, I am not 8 milliseconds or roundabout. And as we have learned, this is much too late for the very fast 1 out of 1 algorithm. So you can apply it. It's CPROTEC 5 standard functionality, but we have disabled it because it has simply no use for the very fast busbar differential protection. And therefore, of course, we have the fast current sum supervision, that the sum over all currents will be 0 every time, which is very quick, which is working on instantaneous values, and which will block immediately within 1 millisecond. But the standard CPROTEC 5 CT loop will pick up only after 8 milliseconds, and that's too slow for the busbar differential protection. But this, all the supervision things will come session 3 or 4. Anywhere, but it will come in one of our next sessions.
Thanks. And then the next question is around what we talk into a reading system. So somebody wants to have the script, and I think we'll take that into account into our next discussions, because we want to improve on that. And I think we will need to think about handing out our scripts so that you can not only listen to us, but also read what you tell. The notes are already there. We'll think about that. So VB, stay tuned. And then AA, could you submit a block diagram of the different self-adapting algorithms?
I guess they
Okay, right?
mean, and this was one of the slides I have tried to explain very long, and this slides will be available, and here you are. It will be available after the session, I guess.
Thanks. So yeah, we will submit that. And when you said that for impedance grounded network, the device used V0, right? Voltage zero criterion.
Yes.
This means that we have to connect the VT to the, does this mean that we have to connect the VT to the 7SS85?
Will you answer?
Yes, I can take this one. Yes, for this criterion, of course, you need the voltage. And if you have a centralized setup or the IEC 61850 compliance solution, you can connect the voltage directly to the 7SS85. If you have this 7SS85CU approach, then you connect the voltage to one of the merging units, and then transmit a signal about the voltage release to the 7SS85 central unit.
Thank you. And I think before our break, we will take one last question. So Arvi, once again, and wants to know, you said that the tripping time is for centralized busbar. What are the tripping time for process busbars?
Yeah, it depends a little bit when we go back to session 1, what kind of process bus for the full distributed solution, which is also a process bus solution, you have to add about 2 milliseconds communication delay. And for the IEC compliant solution, it's a little bit more because the goose, the tripping signal via goose needs a little bit more time, then you have to add around about 4 or 5 milliseconds. So, but nevertheless, faster than the 752.
Okay, thank you. It was not all questions answered. We know that, and we will deliver answers either audible during this ongoing tutorial or later on in a written format. But for now, I think all of you out there listening intensively to what the experts tell you, and a bit for us here in the studio, we will have a short break. I'm not sure, 5 or 10 minutes. How long? 10 minutes? So for about 10 minutes, get yourself a tea or a coffee, whatever you need. Give your eyes a bit rest and take a look outside, see how the weather is there. And so, yeah, we'll meet each other again in about 10 minutes. Thank you so far, and see you later.
Jetzt bist du an.
Okay, so welcome back. I hope you had a little rest for your eyes or eventually checked some mails in the meantime to now concentrate back again, because we already learned that it's kind of a lot of information we delivered to you. So thanks again for joining back in. And the next parts we'll talk about or we'll present to you. Yes, I'm waiting.
You're somehow muted. Your micro is...
My mic is muted.
Yeah.
I didn't do anything. But I'm going to check. Better?
No.
No, not yet. So I'll turn it off. And Let's see.
Should I jump
Better?
in?
No better? Take one of, no, it's better?
Yeah.
Well, so once again with the correct one. So yeah, so my microphone had still been in the break and muted unintentionally. Sorry for that. So thanks for being back. Now I think I and my microphone are back with you. And yeah, let's see, what can you expect from us in this next part? Nina will start with some insights into check zone protection, and then she will lead over again to Rainer to find out the benefits of the circuit breaker failure protection. But yeah, before we see that, we need to learn something on check zone protection. So Nina, I think we'll change places here and the stage is yours.
So thank you, Michaela. I need the slides. Okay. Yeah, before the break, you already learned something about busbar differential protection and the necessity of the disconnector image. And now with a fresh mind after the break, I want to talk about check zone protection. I would like to start by explaining how the check zone works. Then I will explain the differences to the selective zone. And finally, let's look at 2 examples. Here in the slide is our well-known setup. We have a double busbar with 4 feeders and 1 coupler. In the first feeder, the left disconnector is closed and therefore it is assigned to the selective zone 2. This is the red one. In feeder 2, both disconnectors are open. Feeder 3 and 4 are assigned to the selective zone 1, the blue one. The coupler CT is assigned to both measuring systems. Now, additionally to the 2 selective zones, there is a check zone. This is meant with the green dotted area. The check zone is like the overall measuring system, where all 4 feeder currents are included independently of the disconnector positions. Okay, let's go through all the bays and check their assignments. The first one is assigned to the selective zone 2 and to the check zone. That's why the CT is colored in red and green. In the second bay, both disconnectors are open and therefore the bay is not assigned to any selective zone, but it is nevertheless part of the check zone. Feeder 3 and 4 are connected to busbar 1. That means they are part of the selective zone 1 and of the check zone. The CT color is blue and green. The coupler bay is treated differently. It is not assigned to the check zone. It is only assigned to the 2 selective zones and is therefore highlighted in red and blue. In general, currents flowing to the busbar have a positive sign, currents flowing away a negative sign. The picture on this slide is the tripping logic for 2 zones. So bus zones 1 operates if there is a trip command from the selective zone 1 and a trip command from the check zone. And of course, none of the supervision functions should be active to block the tripping. For bus zone 2, it is the same. You always need the trip signal from the check zone to release the tripping of the selective zone. According to this, the check zone protection is an additional security against malfunctioning due to problems with the disconnector image. As with the differential protection, for the check zone protection, a stabilizing current and a differential current are calculated. However, the calculation is different. For the stabilization current, you take the sum of the magnitudes of all the currents that are flowing to the busbar, and you take the sum of the magnitudes of the current that are flowing away from the busbar. The smaller of the 2 values is used as the stabilization current. The differential current is the sum of all currents with signs, not just the magnitudes. This slide shows the different calculation methods of selective and check zone in comparison. The difference lies in the calculation of the stabilization current. Imagine there is only 1 current in 1 feeder flowing towards the fault. For the check zone, the differential current is the magnitude of this current I1. For the stabilization current, you must compare the current flowing towards the busbar equals I1 to the current flowing away equals 0. The smaller value is 0, and therefore this is our stabilization current. For the selective zone, the differential current is also the magnitude of I1, and the stabilization current is the same as the differential current. Okay, I assume now everyone has the question of why in mind. Why is the calculation of the stabilization current different? With this slide, I would like to try to explain that. Let's have a look at the example on the slide. Imagine there's a fault on busbar 2. For bus zone 1, everything looks fine. The inflowing current is equal to the outflowing current, but there's actually a connection outside the busbar protection system in the grid between busbar 1 and busbar 2. The fault is indirectly fed from busbar 1. This is meant with the connection between the two busbars. In this case, the differential current would be the current flowing to the busbar 1 in the first feeder, minus the current flowing away from busbar 1 in the second feeder, plus the current flowing towards busbar 2 equals 1 time the current measured in all 3 bays. The stabilization current would be 3 times this current if you calculate it the same way, like for the selective busbar differential protection. This would lead to an overstabilization and therefore to an underfunction. If we calculate the stabilization current like we learned before, the sum of all currents flowing towards the busbar equals 2 times the current. The sum of all currents flowing away equals 1 time this current. The smaller value is 1 times this current, and therefore we are in the tripping area of the check zone protection. Okay, let's look at some examples. Feeder 1 and 2 are connected to bus zone 2. Feeder 3 and 4 are connected to bus zone 1. The coupler is open, so we have 2 independent systems. There is current flowing towards the busbar in feeder 2 and feeder 4, and away from the busbar in feeder 1 and 3. Okay, let's put some numbers on that to make it less abstract. Let's say in bay 2, 2 kiloamps are flowing towards the busbar 2, and the same current is flowing away in bay 1. Everything is fine with busbar 2. 1 kiloamp is flowing to busbar 1 in bay 4, and the same current is flowing away in bay 3. This is also a stable fault-free condition on busbar 1. In this case, the sum of all currents is 2 kiloamps plus 1 kiloamp minus 2 kiloamp minus 1 kiloamp equals 0. For the stabilization current, we must calculate the sum of the magnitudes of all the currents flowing towards and away from the busbar. The currents flowing to the busbar are 2 kiloamps in bay 2 and 1 kiloamp in bay 4. The sum is 3 kiloamps. The currents flowing away from the busbar are 2 kiloamps in bay 1 and 1 kiloamp in bay 3. The sum is also 3 kiloamps. So in this case, both values are equal, and therefore the stabilization current is 3 kiloamps. Okay, now let's assume there's a fault on busbar 1. The current direction in bay 3 changes. From bay 3 and bay 4, there's a current flowing towards the fault. The current in bay 1 and 2 stay the same. So the currents flowing to the busbar are 2 kiloamps in bay 2 and 1 kiloamp in bay 3 and 4. The sum is 4 kiloamp. The current flowing away from the busbar are the 2 kiloamps in bay 1. So in this case, the differential current is 2 kiloamp plus 1 kiloamp plus 1 kiloamp minus 2 kiloamp equals 2 kiloamp. For the stabilization current, you must compare the 4 kiloamps flowing towards the busbar in bay 2, 3, and 4 with the 2 kiloamps flowing away in bay 1. The smaller value is 2 kiloamps, and this is our stabilization current. These conditions would lead to a trip from the check zone. Okay, yeah, short recap. Ryan spoke about the protection algorithms of the selective busbar differential protection. I spoke about the disconnector image and the check zone protection. These three parts together are all you need to know about busbar differential protection, but you all know this is not the end of this webinar. We still have almost 2 hours, including a break and the Q&A parts. And yeah, the 7SS85 has also other very important functions, and that will be presented here as well. Rainer will now tell you about circuit breaker failure protection, and then I will come back with a part about end fault protection and the coupler differential protection. So I hope you stay all in the meeting, and I see you later.
Yeah, thanks, Nina. So, as Nina already told, there's some backup functionality which are very important, and backup functionality which is really very useful to be used in a busbar protection device is a circuit breaker failure protection. As the circuit breaker failure protection takes a very big advantage of the integrated disconnector image of a busbar protection device. But let's come to the details. So, circuit breaker failure protection. What I start maybe as an introduction, we have in the busbar protection, and that's a little bit different compared to the other Supertech 5 devices. We have two types of busbar protection. I start with a busbar protection which is common to all Supertech 5 devices. And I will also explain about the inherent circuit breaker failure protection, which is a little bit a special type of circuit breaker failure protection only available in the busbar protection. But let's start now with the advanced circuit breaker failure protection. I have here a short example. We see here a double busbar with 4 feeders. It's a double busbar, and we have an 7SS85. It could be a centralized busbar protection, or it could be the central unit of distributed busbar protection with an integrated disconnector image. And now I am struggling. Oh, sorry. I'm struggling a little bit with my animation. Give me some time. Yeah. Okay, we will start here. What is blinking here? This big error. Thanks, Nina. Here is a circuit breaker failure protection. The circuit breaker protection function, which is assigned to this certain feeder here, which is assigned to bay2. It could be a function in the centralized busbar protection, or the circuit breaker failure protection in case of a distributed busbar protection could also be assigned in the merging unit or in any modular Supertech 5 device. And once again, here is a 7SS85, which could be the centralized 7SS85, or which could be the central unit of a distributed approach. And we have an external feeder protection device. And this could be a Supertech 5 device, it could be a line differential protection, a distance protection, overcurrent protection, transformer protection, or anything else. And this external device is detecting a fault. And it will send, you will see here the feeder protection, and this red blinking line, and together with the mouse of Nina, will send a trip signal to coil 1 of the circuit breaker And in parallel, you see it here to this other red blinking arrow, it will start the circuit breaker failure protection in this circuit breaker protection function in the 7SS85 or in the merging unit of the distributed busbar protection. Then this circuit breaker failure protection will start. And what I explain now is really the same algorithm, the same code for all Supertech 5 devices. we have a current threshold and we have a delay time T1, which is blinking here. And the device, the function is monitoring the current, whether we are above or below this current threshold. If we are below this current threshold, all is fine. The circuit breaker is working, the current will drop to 0, everything is fine. If not, if we are after delay time T1, we are still above the threshold, we will, it's a setting, it can also be used without trip repetition. Let's assume we have, according setting, a trip repetition, and then we will try a trip repetition after delay time T1. This now you will see here with this red blinking errors. And now, so typically with coil 2 of the circuit breaker failure protection, we will send the trip signal to coil 2. Okay, let's assume we try the trip repetition. Nothing helps, and then we will wait until delay time T2. We will still monitor the current, whether we are below or not. If it's now maybe the trip repetition brought the result, the circuit breaker is open, the current drops below the threshold, everything is fine. If not, after delay time T2, we will have the signal trip T2, which can be used also for an transfer signal to the other end of the line to clear the fault. But we will also send, next step, we will send an internal signal via directly in the centralized busbar protection or via communication or via fiber optics from the bay unit, merging unit to the central unit. We will send a signal to the 7SS85. And according to the disconnector image in the 7SS85, which knows exactly we have the faulty feeder, the feeder with the faulted circuit breaker. Here sits this busbar 1, the upper busbar. And according to the disconnector image, the 7SS85 knows, okay, to the same bus zone, bay 1 and bay 4 is also assigned. Bay 3 is assigned to other busbar, so we don't have to trip it. So it will trip the associated bus zone. By the way, maybe a good idea first time to mention it here. Now the 7SS85 trips after circuit breaker failure protection bay 1 and bay 4. And in 10 minutes, I will call about the inherent circuit breaker failure protection. It's important to know that also now in bay 1 and bay 4, the inherent circuit breaker failure protection will be started. That was, sorry, I forgot, but in Bonsab, that's the procedure, the way it works in the so-called iQuery mode, because here we have really the current threshold of the circuit breaker failure protection, and if the current is above the threshold, we will trip the bus zone according the disconnector image. That's the iQuery mode. We have a second mode of the circuit breaker failure protection in the 7SS85. That's the so-called unbalancing mode. It's most of the things are absolutely the same like what I have explained before. We have a circuit breaker failure protection function assigned to a feeder, which could be in the central busbar protection or in the merging unit. And we have the 7SS85, which is its tripping characteristic, which could be the centralized or it could be also the sender unit of a distributed busbar protection. We have, once again, a feeder protection device, line protection, transformer protection, anything else, which detects a fault, and it tries to trip the circuit breaker of bay 2. And once again, in parallel, it starts the circuit breaker failure protection in the merging unit 7SS85 circuit breaker failure protection function. We have once again our current threshold. We have delay time T1, watching the current information. If the current don't drop below the threshold, the device, and we have a trip repetition, the device will send a trip signal to call 2 of the circuit breaker. If this doesn't help, we will wait until delay time T2, whether the current will drop now. If nothing helps, once again, and up to now, up to before, everything the same with the same function for all the Protect 5 devices. And now the enhancements of the circuit breaker failure protection for the busbar protection starts. We will send once again a signal to the 7SS85 function group busbar protection, to the 7SS85 central unit. And now we are not directly tripping according to disconnector image, the bay 1 and bay 4, because we are now in the unbalancing mode. And in this unbalancing mode, we are doing a different thing. We are sending a signal to the 7SS85, and in parallel, you see here the current threshold. This current threshold will be sent to the 7SS85 function group busbar, to the characteristics, and this current threshold multiplied with 2 will be the minimum differential current threshold for the thing. And in parallel, the device is unbalancing, means it's multiplying with -1 the current of this feeder current. And then, via the normal algorithm with the same mechanisms of the busbar differential protections, the device is looking whether we are in the tripping area or not. Once again, it will be not the characteristic with the same minimum differential current threshold for the busbar differential protection. The minimum differential current threshold will be the current threshold of the specific feeder setting multiplied with 2. And the stabilization factor will be 0.5 every time. And then, via the normal mechanisms of the busbar differential protection, the device will trip according to disconnector image, here in this example, bay 1 and bay 4. The advantage of the unbalancing mode is a very short reset time. So that means you say, even if the current drops immediately after delay time T2 has worked, and after delay time T2, suddenly the current starts to drop out. We will once again, together with sampled measured values, it's still enough. We will not wrongly trip the busbar, the complete busbar, because of this very short reset time. And okay, the reset time of the feeder protection, the reset time of the transformer protection device or anything doesn't matter. So we have really the same security as with the busbar protection device. So I know, okay. Okay, now these questions. I thought we made it at the beginning. So one question before I come to the end, and I will explain also the other functions and the inherent circuit breaker failure protection. What do you think? That's a little bit repetition of also my first part of the busbar protection algorithm. If we have this unbalancing mode, so we are unbalancing the feeder current and the circuit breaker failure protection is in the unbalancing mode, which of the algorithms, which of the 3 algorithms, the 1 out of 1, the 2 out of 2, or the filter algorithm, will trip after the unbalancing, after the trip 2 in unbalancing mode. So you will have around about 10 minutes to think about it, and then we will have a look to the answer. Will exercise for me how could I explain the algorithm in the part before. The circuit breaker auxiliary contact criteria for these guys who still living a little bit in the wording of the 7SS52. Here's the circuit breaker auxiliary contact criteria was called the low current mode of the circuit breaker failure protection. The circuit breaker failure protection with auxiliary contact criteria should be used in case of external force with a very low feeder current, where the current is no really trustable, reliable criteria whether the circuit breaker is on or not, especially after an Buchholz protection trip. So the acquisition of the circuit breaker auxiliary contacts will be done by the normally open and normally closed contact, just in the same way as Nina has it explained for the disconnector image. A little bit different is once again for the still a lot of people who know very good the 7SS52. We had done a slightly change in our philosophy. That's because now we are really in a protection family, Protect 5, whereas 7SS52 was a little bit its own world. In Protect 5 and the 7SS85, the going normally open contact stops the circuit breaker failure protection, whereas in the 7SS52, the coming normally closed contact stopped the circuit breaker failure protection. Sometimes maybe important difference. As this is here very important, you know, circuit breaker failure protection here can trip because of a wrong signals, a whole busbar. We should use every time both the normally open and the normally closed contact to have the advantage of the supervision of the circuit breaker auxiliary contacts. And this will block automatically the CP position if it's not possible, if we are after the supervision time in the running state, or if we are in the disturbed state, if we have 0-0. So, okay, and we have specific logic with current threshold modes for dropout applicable. Very important, because during the last weeks I have very often these questions. If you enable the auxiliary contact criteria in the Protect 5, you will nevertheless every time have available also the normal current threshold criteria. So let's assume we have enabled the auxiliary contact criteria in this circuit breaker failure protection function. And we have nevertheless a current threshold of, let's say, 0.5 of the nominal current. And if we start now, if the circuit breaker failure protection has been started and the current is below the current threshold, then the circuit breaker failure protection function will work with the auxiliary contacts. But if the current at the moment of the start is above the current threshold, we will nevertheless work with the current criteria, as the current criteria is a more reliable criteria for circuit breaker failure protection. So that's also very important. It's common to Protect 5, a very important information. Inherent circuit breaker failure protection. I have already mentioned in this example, when we, after trip T2 of the circuit breaker failure protection, and according with the disconnector image, we tripped busbar as a circuit breaker in bay 1 and bay 4. And here we will start the inherent circuit breaker failure protection in the circuit breaker. So the inherent circuit breaker failure protection will start for all internal trips of the 7SS85 of the busbar protection device. Means it will start after a trip of the busbar differential protection, after the trip of the circuit breaker failure protection, after trip T2 of this one instance. So when we trip the whole busbar, and it will also be started via external trips via binary input. It can be kept also by a normal bay current. So you have, once again, the normal current threshold. You will not have a trip repetition. It makes no sense because you have tripped anyway. You will have only delay time T2. And that's important. If we are in a feeder bay, the inherent circuit breaker failure protection will provide an inter-trip signal, which can be used to clear the fault at the other end of the line. So inherent circuit breaker protection start in the feeder bay, and after delay time T2, we will have the trip T2 of the circuit breaker failure protection, which can be used to send a signal to the other end of the line to trip the fault there. And if we have coupler bays, we start the inherent circuit breaker failure protection in a coupler, and we have once again the delay time T2. And here, after, if we are still above the current threshold, after delay time T2, we will unbalance the adjacent busbar to trip the associated bus zone in case of a fault of the circuit breaker in a coupler. And of course, we have also here in this case a zone selective tripping in case of the coupler bay when the inherent circuit breaker failure protection is in a coupler. There's no setting needed. You have the inherent circuit breaker failure protection in its bay, and it will, according to the configuration in the single line, in the next two sessions, session 3 and 4, we will show you how to configure with DXC5 a centralized busbar protection or a distributed busbar protection. And the device will recognize by itself whether the inherent circuit breaker failure protection is in the feeder bay or in a coupler bay and will react accordingly. Bay-specific settings, of course. The current thresholds has to be adapted depending on in which feeder, in which current it's working. Inherent means also for the internal trips and inherent for the inherent circuit breaker failure protection. You don't have to pay function points. Whereas for the advanced, for the externally started circuit breaker failure protection, you have to pay some function points depending on whether it's a 3-pole circuit breaker failure protection or a 1-3-pole. Last but not least, circuit breaker failure protection with external circuit breaker failure relays. So that's sometimes a requirement. I know it quite well in a lot of customers in the United Arabs that they want to have their separate circuit breaker failure protection, means this whole logic monitoring the current threshold, delay time T1, delay time T2. This is all handled in an external device. And when it's finished, they only want to use the disconnector image of a busbar protection device to trip the associated bus zone. And therefore, we have this functionality of the external trip in the circuit breaker failure protection. You can both use an external trip from a bay. So you will send an external trip to a bay, and it will trip the bus zone where this bay is assigned to. Or you can also use an external trip directly to a bus zone. And here, common, this external trip to a bay is typically triggered by an external circuit breaker failure protection device, I have said, and it's using the disconnector image of the busbar protection. And we have the zone selective tripping, and very important what I mentioned to say, with an external trip, you should think about it, that with one binary input, that's one signal, you are able to trip a whole bus zone. That's quite dangerous, and you should really think about it, that with one binary input, it will be possible to trip a whole bus zone. And therefore, we strongly recommend to use not only one binary input, but to use also at least 2 binary inputs and to use this additional release contact. So typically, the external trip will come from this external feeder protection, from this external circuit breaker failure protection device, and the release contacts, the release input, typically will be done by the pickup of the protection functions, the pickup of the overcurrent protection or anything else, to have an additional security against the wrong tripping by using this external trip. So that was my part of today. Let me see how was the result of the exercise. So 30% thinking it's a 1 out of 1 algorithm, and 58% thinks it's a 2 out of 2 algorithm. So I could be quite proud. At least the majority of you answered these questions right, correctly. It's a 2 out of 2. Why not the 1 out of 1 algorithm? Because the 1 out of 1 algorithm needs to be triggered by a jump of the stabilization current. And such a jump of the stabilization current can't happen in case of such a circuit breaker failure protection trip, because the fault, the jump, has already been happened when the feeder protection device had tried to trip the circuit breaker of its assigned feeder. So here we had a jump. And if a typical delay time, T2 of the circuit breaker failure protection is 100, 120 milliseconds. So the jump of the stabilization current to trigger the 1 out of 1 algorithm has been passed already around about 100, 120 milliseconds. So the 1 out of 1 algorithm is not possible, but the 2 out of 2 algorithm will trip in this case. So now I am finished for today. I just have to answer maybe some questions. And I like to welcome Nina to tell us some very interesting things about endpoint protection.
Fragen kommen noch.
Yeah,
We have
but
a
before
Eckhart.
Rainer, you are not yet
what a
done
pity.
for today. I have questions.
You have
for
questions.
you.
I thought at the end on
Yes,
there.
yeah, we have one more round of questions right now. And I think we will have one short break again, because that's a lot of input for all of our heads. So we take about a 10 minutes questions round once again, and then after that a short break, and then we'll be back with Nina. But now, still here in the studio.
Okay.
And I think we start right now with the newest questions first. So why the circuit breaker failure inherent doesn't have a retrip time, doesn't have retrip, in brackets, time T1?
Yeah, okay. Why we have, because anyway, the inherent circuit breaker failure protection will every time start when we have already and try to trip the circuit breaker before anyway. And so typically, and for example, busbar protection, typically busbar protection every time, no doubt about it, most customers will immediately trip call 2 and call 1 at one step. Because for busbar protection, we have to clear for any case as soon as possible. And as you have anyway already tried to trip both calls, it makes no sense to try once again a retrip to only call 1.
Oh, okay. Thanks. Yeah, makes sense. And next one, what happened from CP? So what happens when I have the 2 criteria of the BF, but I get a 0, 0 or 1, 1 position from the auxiliary contacts of the circuit breaker? And you need to help me out again. What's the BF? The B for busbar?
Breaker failure, I guess.
Breaker failure. Oh,
Yes,
thanks. So it's circuit breaker failure.
I guess they mean with the 2 criteria, both the current criteria and the circuit breaker failure protection criteria. But I get a 0, 0. It's something about the auxiliary contact criteria, I guess. I do not know what exactly with this 2 criteria. But if it's 0, 0, and it's above the supervision time, the circuit breaker failure protection will be blocked. So that means you will have no trip T2 of the circuit breaker failure protection when you have a non-plausible state of your auxiliary contacts.
Yep. Okay, Nina, something to add there? No,
No,
fine with
all
that.
fine.
Sorry. So, and then TDM wants to know, does the circuit breaker failure on the 7SS85 CU, so the Bay Unix 6 MU85, have the same algorithm as the conventional 7SS85?
Conventional. The conventional, I guess he means the centralized busbar protection. But as I have stated, the algorithm until trip T2, this current threshold, delay time T1, T2 auxiliary contact criteria, will work in case of the 7SS85 CU every time in the merging unit, not in the 7SS85 CU. But the algorithm, the logic, how to trip according the disconnector image, whether you're in the unbalancing mode or in the iQuery mode, that's exactly the same in the 7SS85 CU, like in the centralized busbar protection 7SS85. Yes.
Okay, thanks. The next one I see here from RA is not a question, is it's a statement. 7SS85 will have BI, so binary inputs for transformer mechanical protection, breaker failure initiation. Is it that's not really a question? So if we get a question out of that, please place it again. But the next one is almost a question, and I put it like this: is there any difference in the breaker failure function between the 7SS85 and the 7SS522, 523?
Basically not. Besides this one, the stub of the circuit breaker failure protection with the auxiliary contact, I have already explained that there is a difference. There are no big differences, but there might be also very small difference really in the details. And for especially it's mentioned, the 7SS85 has the same breaker failure protection like all Cyberdeck 5 devices, and there are some very small differences are possible.
Okay, thank you. And the next question comes from VB. Does the inherent 50 breaker failure,
Circuit breaker failure protection,
protection capable to start or to work without the current query? The case is the feeder protection issues a trip command for circuit breaker of a non-loaded power transformer and the circuit breaker fails to open. Oh, that's a scenario.
Yeah, okay. I guess this question has been written before I explained the circuit breaker failure protection mode with the auxiliary contact criteria.
Probably.
Because here exactly, I have also explained it will work when possible, nevertheless, every time with the current criteria. But in this example, he will have no current flowing at all. So it will work absolutely for sure in the auxiliary contact criteria. And so I see simply the answer is yes. It will work without current criteria if you are activating the auxiliary contact criteria in the circuit breaker failure protection function.
Okay, thanks. And VB placed one more really new or current question. So the 7SS85 going no stops normally open, or it's not a no. Thanks.
No,
that's why
no,
we have
it's not a no.
experts here. It's not a no. It's a normally open. Yeah, that's what happens with these abbreviations. But you know what to read there. So I'll start again so that everybody understands the question. The 7SS85 going normally open stops the breaker failure protection. Do we need the monitor to monitor the MCB, mechanical circuit breaker, which is simply supplying the binary inputs of the busbar protection system? So a plausibility check. Did you Do you understand the question? If not, we'll take it offline and
not
ask
in
for more
detail,
information.
but
MCP means the mini circuit breaker. Sicherungsautomat.
Oh, like a fuse. Okay.
Which is swapping the binary inputs. Yes, in principle, you should monitor. As I have said, you should use both the normally open and the normally closed contact. And if they are for a certain time, for a longer time, so if here, as Gerd has said, you have no auxiliary supply, you will pick up the supervision time, and then the circuit breaker failure protection will be blocked. So definitely, yes, you should monitor by using both the normally open and the normally closed contacts. That's our recommendation.
Okay, thanks. And I think then we are in the round of questions that were still part of the first set during today's tutorial. So we take this one in the process bus.
For this first question, the answer is yes.
Okay, but I will read it.
Okay.
So that was much faster. And now our auditorium has no idea what you will answer. It's like the 42. And I'll deliver the question. So in the process bus, with a 7SS85CU system, are the actuation system of the first half and the second half cycle the same? So n equals 1 and n equals 2. The same. And I remember the answer was yes.
Yes, I guess. I think the question is not so very clear, but I guess and I hope it's regarding this 2 out of 2 algorithm. So first half to be in the trimming area and second half. And I assume that's the question about this first half, second half of the 2 out of 2 algorithm. And here the answer is the Busbar differential algorithm I have explained 2 hours ago, completely identical. It's not only completely identical, they're really the same. It's the same code. It's the same in the 7SS85CU. It's the same in the centralized 7SS85CU. It's absolutely the same.
Mm-hmm.
No difference.
Thanks. And here's one that I find really interesting. It was there. When retrofitting, from AA, the question, when retrofitting a substation with a dismantled old HITEC, so it's high impedance busbar protection, the early make or late break contacts, can they be used without problems in the new low impedance relay?
This early make, it's not so easy. I know an application note from my predecessor, Hans-Werner Funk, where in detail he checked it, whether it may be a problem. And I would say basically, yes, it can be used. But to be on the safe side, when I will answer these questions, I will have once again a look to this very old, very detailed application note of my predecessor.
Perfect. So you see, here are experts talking to experts and asking brilliant questions. So we'll have an answer on that with a nice, great foundation of knowledge. And a next question coming from RV. Do we need disconnector image for a double busbar substation with a coupler, but only one disconnector for the feeder in order to know which busbar is the fault? I think you need to read that again, or even me.
One disconnector.
Feeder,
so
once again.
This question is a little bit confusing to me.
Okay.
Because it's a double busbar, but you have only one disconnector. So if you recapture what we have learned 5 weeks ago in our first day, you need a disconnector image every time when it's possible to assign a feeder current to different bus zones. Mm-hmm. And then, of course, you would need 2 disconnectors in one feeder, because otherwise you can assign it only to one of the bus zone. What you do not need, so basically couplers if you have disconnectors and the couplers, that will not cause that you have to pay a device with disconnector image. But I guess we need a little bit more information, so that's not very plausible. These questions. Maybe we have to come together to discuss it directly.
Okay, thank
So
you.
there's some inconsistency check in my mind, and therefore I can't answer.
Okay. Yeah, so plausibility.
Yes.
Thank you. So we take one last question before we go into a short break, and that's the one about frequency. From TDM, it came in. Does the 7 essays, you need to listen to me, Gert will need to find that. Yes. Does the 7 SS85 CU protection work normally at 60 Hertz? So 4000 Hertz collaboration rate and 1 S2 ESDU. So just...
Do you want to answer?
Yes.
That was simple. So 50 Hertz, 60 Hertz, no problem. We can.
I guess we had the same questions in our last tutorial.
Yeah, I mean, we have new ones.
At least I answered.
Yeah.
So maybe I know also where the confusion comes from. That this sampling rate 4000 Hertz and 1 ASDU is via IEC mainly recommended for the 50 Hertz system. And now they had doubt about to use it also in the 60 Hertz system. But I can absolutely confirm we have done several RDTS tests. It will work absolutely fine also in a 60 Hertz system.
Perfect.
So no problem.
So perfectly fine is just perfect for a short break. We'll meet again in about 10 minutes, and 5 minutes before the restart, you will see that once again on the page. And thank you so far, and stay tuned because Nina will tell you what you need to know about end-fault protection. So see you in a few minutes.
Bye-bye.
So let's go again. Last round for today. Last but not least, no, we've seen Nina for a few times quite now, and she will tell you, she will share your knowledge about end-fault protection and tell you what you need to know about end-fault protection. And once again, Nina, the stage is yours.
Okay. Thank you, Michaela. So, final sprint in this quite challenging session. Hold on for another roundabout 30 minutes. I will explain you something about end-fault protection and bus coupler differential protection. But first, we start with two warm-up questions. Do you have your CT's line side or busbar side at your substation? Please scan the QR code or copy the link from the chat. Second question, do you use end-fault protection in your feeders? Once again, scan the QR code or copy the link. If I was too fast changing the slides, please check the chat for the link to the question. And yeah, I will give you now some time to answer it. Okay, this slide is full of facts about end-fault protection, and the details will follow then. With end-fault protection, the area between the circuit breaker and the current transformer is meant. End-fault protection is in function in the function group circuit breaker. End-fault protection is only activated when the circuit breaker is open. When active, end-fault protection removes the respective current from the selective zone measurement. And for a feeder with CT on bus side, end-fault protection removes also the current from the check zone. The circuit breaker auxiliary contact normally open and normally closed, and the circuit breaker close command are required for this function. The treatment of the normally closed and normally open contact is comparable to the disconnector image. The normally closed contact is the important one for the position acquisition. The normally open contact is for supervision. It is important to wire the circuit breaker close command, which deactivates the end-bar protection, so that the feeder current is considered in the busbar protection. I will come to that point later. If you have the normally closed contact and the normally open contact available, the supervision of the auxiliary contacts is possible. End-fault protection requires function points. The most important points on the slide are marked in blue. Please keep them in mind at least till the end of the session. End-fault protection is only active when the circuit breaker is open. When active, it removes the current from the selective zone measurement and also from the check zone measurement if the feeder CT is bus-sided. To get a better understanding of the end-fault protection, we will go through different use cases. We start with the feeder with the CT on bus side. That means the circuit breaker is behind the current transformer from the perspective of the busbar. Then we come to a feeder with a CT on line side. And then we talk about end-fault protection in a coupler with 2 CTs and 1 CT. Okay, let's start with the feeder with the current transformer on bus side. The measuring range only goes down to the CT. So a fault between the circuit current transformer and the circuit breaker would be an external fault for busbar differential protection. The feeder protection recognizes the fault but cannot clear it because it is fed from the busbar. So without end-fault protection, the fault clearance time would be delayed because you have to wait, in example, for the circuit breaker failure protection or a subordinated protection. With end-fault protection, the feeder current is removed from the bus A measurement and from the check zone measurement. That means the current is set to 0 when end-fault protection is active. And the check zone because the fault is fed from busbar A. The differential current leads to a fast trip from busbar differential protection. That means the measuring range is extended down to the circuit breaker. Okay, now the team must show me the slides again, please. And not the results.
Sorry.
Okay, thank you. The second scenario we want to look at is a feeder with the CT on line side. The measuring range from the protected zone goes down to the CT. So a fault between the circuit breaker and the current transformer looks like an internal fault for the busbar A. But since the circuit breaker is already open, the fault cannot be cleared by switching off the busbar. So a bus A would operate unnecessarily. In this scenario, without the end-fault protection, there's an overfunction of busbar protection, and you have to wait until the protection at the remote line side actually clears the fault. This can, of course, take some time. With end-fault protection, the feeder current is removed from bus A measurement. Consequently, there is no differential current for the selective zone A and no unnecessary trip. In this use case, since firmware version 8.40, the feeder current is not removed from the check zone. The result is the same, because if there is no selective zone trip, the busbar protection will not trip regardless of the check zone. But it has an advantage, which I will explain in a moment. With the trip of the end-fault protection, an inter-trip signal can be sent to the remote end for a faster fault clearance time. I mentioned earlier that it's important to wire the circuit breaker close command if you have end-fault protection in use. Please imagine the following scenario. We have a feeder, the circuit breaker is open. The end fault protection is active. The circuit breaker is open because there was an external fault on the line. Now there's a close command to the circuit breaker, an example from auto reclosure. Current starts flowing, but the auxiliary contacts are slower and the circuit breaker position is not yet detected as closed. That means the end fault protection is still active and the current is removed from the measuring system. For the busbar protection, this looks like an internal fault and this leads to an unnecessary trip. Rainer told me from his experience, this happened like once or twice a year that the customer reported such an, in quotes, small trip. The solution is easy. The closed command for the circuit breaker must be wired to the respective binary input signal closed command. As soon as the signal is received, the measured currents are made available to the busbar differential protection. What I just explained in general for a feeder, I would now like to apply specifically to the use cases CT bus side and CT line side. Then it should also be clear why we remove the current from the check zone in one case and not in the other. Let's start with the CT on bus side. The scenario is the same. There was an external fault, the circuit breaker is open. A closed command is active, and the current is already flowing, but the circuit breaker is not yet detected as open. If the CT is on bus side, the current is removed from the selective zone and the check zone. That means there is a differential current for both measuring systems and the trip command is released. In this scenario, wiring the circuit breaker close command is really important. Okay, now the current is not removed from the check zone. That means there is only a differential current in the selective zone, but not in the check zone. Therefore, the check zone blocks the release of the selective zone trip. And this is the advantage of the implementation since version 8.40. Nevertheless, always get into the habit of wiring the close command. Yeah, enough about feeders. Let's take a closer look on the bus couplers. First, I want to talk about a bus coupler with two CTs. The circuit breaker is closed between them. The CTs are assigned in an overlapping mode. That means the left one is assigned to bus A, the blue one, the right one, is assigned to bus B, the red one. Therefore, the area between the two CTs, also called dead zone, is part of both measuring systems. In case of a fault on position 1 or position 2, both selective bus zones will trip. That means you have a very fast but non-selective fault clearance. Okay, now let's assume the circuit breaker was open before the fault and the fault happens in the stub A, the area between the circuit breaker and the right CT. Without end fault protection, the behavior would be the same as on the last slide. Both selective zones will trip. With end fault protection, the current from both CTs is removed from bus A and bus B measurement. That means for bus B, there is no longer a differential current since the current of the right CT is removed and the fault is not fed from bus B. There is no unnecessary trip of busbar B. The current measurement from the left CT assigned to bus A is also removed. But since the fault is fed from busbar A, there is a differential current and the selective zone A trips. The fault is cleared fast and selective. On this slide, a picture of a coupler with only one CT. The CT is assigned to both measuring systems. The circuit breaker is closed and fault protection is not active. A fault on position 1 between CT and CB looks like an internal fault for busbar B and like an external fault for busbar A. System B trips, but the fault is not cleared. Let's assume the circuit breaker has opened and we have no end fault protection. For bus A, nothing has changed. It still looks like an external fault. Since bus B has tripped and the fault is still there, the inherent breaker failure protection is started. Finally, the fault is cleared by the inherent circuit breaker failure protection, sending a trip command to bus system A. Now we have the same picture once again, but let's assume the end fault protection is active. Consequently, the current from measuring system A is removed, and this leads to a differential current since the fault is fed from bus A, and therefore to a trip of the selective zone A. The fault is cleared. The fault clearance time is significantly shorter than on the slide before without end fault protection. Yeah, so this is all I wanted to explain about end fault protection. Now I want to spend some minutes about bus coupler differential protection, because for a coupler with two CTs in combination with end fault protection is a very good solution for a fault in the dead zone. This slide gives an overview about the possible solution for coupler base with one or two CTs. The scenario we are talking about on this slide is a fault in the dead zone. If you have only one CT, the CT is assigned to both bus bars. This setup of fault between circuit breaker and current transformer is a bit difficult and leads to a long and non-selective fault clearance. With two CTs, you can configure the overlapping mode. That means in this example, the left CT is assigned to the upper bus in blue, the right CT is assigned to the lower bus in red. In case of a fault in the that zone between the two CTs, both bus zones will trip. This means a very fast but unselective trip. If you have two CTs not in overlapping mode, the dead zone is not protected. This is, of course, not a solution. And yet, this is the reason why we need bus coupler differential protection for selective fault clearance for a coupler with two CTs. Sorry. The bus coupler differential protection protects the area between the two CTs in a coupler. This area is treated like an additional virtual bus zone, here marked in green. If you have bus coupler differential protection, the setting mode is non-overlapping. The differential current is the magnitude of the sum from both currents. In case of a current flowing through, the sign of both current is opposite, and thus the sum is 0. Now let's assume there is a fault in this green marked area. Then the current is flowing towards the fault, and the direction of the current in the right CT changes. This leads to a differential current greater than 0. Now in the first step, only the CT of the coupler will be tripped. After the circuit breaker is open, the current from the healthy bus zone will be zero automatically. In this example, I1C, the left CT is 0. But the fault is not yet cleared. It is still fed from bus B. And this is the moment where the end fault protection gets relevant. I hope you remember this scenario. For bus B, the fault looks like an external fault because it is behind the CT. As soon as the circuit breaker is detected as open, the end fault protection gets active and sets the current I2C to 0 for the busbar differential protection. This leads to a differential current, and the selective bus zone 2 will be tripped. The advantage of the bus coupler differential protection in combination with end fault protection is a selective tripping. Disadvantage is a delayed fault clearance time compared to the overlapping mode. This may lead to problems in case of high current multi-phase faults, especially when you have a network with a high percentage of non-synchronous generation, in example wind generation or solar power. This can lead to islanding or network splitting. For networks with many classic generators, slightly longer fault clearance times are usually not a problem because the inertia is higher. If you want to go deeper into this topic, we can recommend a paper that discusses this question in which case the shorter tripping time of the overlapping mode is preferable to a selective release of the sequential tripping. Furthermore, it is possible to switch to overlapping mode for high current faults. For this purpose, a threshold value can be set for single pole and multi-pole faults. This slide shows the tripping characteristic of the bus coupler differential protection. The characteristic looks at the first sight similar to the characteristic of the bus bar differential protection. On the x-axis is the stabilization current, on the y-axis a differential current. The green area is the stabilizing area, everything without color is the tripping area. As mentioned on the slide before, you can set two thresholds at which the algorithm changes to overlapping mode, one for single pole faults, one for multi-pole faults. If the threshold value parameter is set lower than the minimum differential current threshold, this results in the corresponding fault type always being clarified quickly and on an unselective basis in overlapping mode. This is meant with the lower dotted line. The upper dotted line is the threshold value for single phase fault. That means in the area between the two dotted lines, multi-phase faults are cleared in overlapping mode and single phase faults sequential with bus coupler differential and fault protection. In the area above both dotted lines, all types are cleared in overlapping mode. Okay, you made it till the end. I know it was a challenging session with a lot to process. Let's look at the results from the questions at the beginning of this part, and afterwards we have time for your questions. So, do you have CTs line side or on busbar side in your substation? I see 30% have their CTs on line side, 13% on busbar side, and the majority of your votes is that they have both configurations, both setups. Thanks for participating. Interesting. And the question, do you use end-fault protection in your feeders? The percentage values are almost the same. We have 47 vote for yes and 43 vote for no, I hope. After this session, it will change and I convince you using end-fault protection. So now we have time for your questions. Michaela, Rainer, will you join me on stage,
Yes,
please?
I will, and I bring some question and definitely an interesting hint already gone, but we will take care of that hint to the slides. I'm muted again. Yeah, microphone is off.
Me too or me not? Passt.
Oh, no.
Passt.
Okay, it's flickering. Let's see if it works right now. Somehow today I've got a bit of trouble with my microphone, but as long as you can understand the experts, everything is fine for me. And thanks for the hint concerning the slides, left side, right side, whatsoever. I think Gerhard will forward that hint, or I hope that he will forward that hint to you, because that was really a useful tip. But now let's see. First question I see here up in the row is from RA. How to connect the mechanical protection, so no current, to start the circuit breaker failure protection?
How to connect?
I think it is about, for example, Buchholzschutz or something like that.
Yeah, I think that's the question is once again the auxiliary conduct criteria, but how to connect?
Maybe you can
maybe how to activate the auxiliary conduct criteria. It's simply a setting. In the settings, there are several settings in the circuit breaker failure protection, and one setting is to activate the auxiliary contact criteria. Then, of course, you need also to acquire the normally open and the normally closed contact. And the start of the circuit breaker failure protection together with the auxiliary contact criteria, it's the same like if you have the current criteria. It's simply a binary input and a signal. This binary input can, of course, be triggered also by a Q signal. And so there's a possibility. Mm-hmm. I hope I could answer. I'm once again not 100% clear.
If we understand the questions correctly, that's sometimes the problem right here. But that's why we try to answer the questions as good as possible.
But as it's mentioned, no current, yeah. I guess it will be how to activate the auxiliary contact criteria.
And if you think your question was not perfectly answered, get in direct contact. Then we have another question already coming.
I guess you have once again maybe.
I need
Take this one.
I guess we need a battery supervision of your micro in the next session.
Yes, somehow. I'm not running out of energy, but my microphone does today. Yeah. So thanks. Thanks for the hint there. And then it's easier for you to understand us. So what did I want to tell you? So if we missed your questions somehow, just get in contact once again. And we have one concerning web access and something like this. I think it's not a dedicated question for this experts tutorial. It's more for the general support, I see, because talking there about Windows 10, we are no Windows specialists at all. We always contact our IT support, to be honest. And now let's see. First question in the row is how to know from SM, right? How to know 2.5 breaker scheme fault in check zone. That's a short question, and I hope that some of my experts will understand it.
2.5 breaker scheme in the check zone. Oh, so once again, very okay. 2.5 breaker scheme. I guess we have answered this in our last tutorial. So it's typically you have an upper bus zone. So for Busbar protection point of view, a 2.5 breaker scheme, there are two independent single bus zones. And then you have your selective zones is the upper bus zone and the lower bus zone. And the check zone includes both. So that's the check zone in 2.5.
Okay.
So it's the answer.
Thanks. Maybe
once again, not 100% clear about this question.
So maybe take a look again into the first webinar and come back to you if the question is still there, right? Okay, thank you. So then Nina mentioned the paper on why an area with a lot of solar and wind generation might be problematic. And I think we will publish the link to the paper, right? It's part of the presentation. So you will get access to the link and can access the paper there. But thanks for asking once again. And another question. That's interesting. In the configuration scheme, using the process bus with a 7SS85CU to carry out the overlapping configuration, would I necessarily need 2 MUs for the transfer feeder?
I'm not completely sure what is meant with transfer feeder, but it is possible to put 2 CTs, 2 current measuring inputs in one merging unit, and it's not necessary to have for each CT a separate merging unit.
Okay.
I guess he came from the 7SS52, and there you make this overlapping with 2 bay units, and you assign the 1 bay unit to the left side, and so you make really this overlapping via wiring. But that is not the case anyway in the 7SS85 because there's a setting since the beginning. And now when we come to the distributed solution, it remains to be a setting. And you can realize this overlapping both with one merging unit, and it's also possible with two. Yes, it's absolutely not connected by using how many merging units. So it's independent from the number of merging units. Both is possible, one and two merging units.
Okay, thank you. So next questions from VM. So shall we use the sensor CT for busbar protection and breaker failure?
Sensor CT, I guess maybe you mean the LPITs. This is our process bus solution, and it's possible for our distributed busbar protection to use also the LPITs. And if you're using the sensor CTs, LPITs, of course, it's simply not possible to use a normal CT for the busbar protection and the other CT for the breaker failure protection. If you use a LPIT, you must use it both for busbar protection and for breaker failure protection.
And you can use it for both,
yes,
right?
You can use it. Our distributed solution is fully integrated in our Cibrotec 5 process bus solution, so you can use it.
Okay, thank you. And then next short question is there busbar thermal protection in the Cibrotec 7 SS85?
So no, no, we don't have thermal protection, and this would be a new requirement for us.
Yeah, but you can add this if you have here this IOs with a thermal input, but you can combine it. It's an optional function in Cibrotec 5. I have no idea how you want to combine it directly with busbar protection, but you can add the normal thermal thing, and you can at least configure some alarming signals or anything else. So that's possible, but it has no deeper connection to the busbar protection.
And now let's see if we can bring this question to you and to our experts. It's a rather long one, and no problem if you understand just half of it. We will send out the answer to that in addition to this audible one. So I try to read that. When you are using one-phase tripping and AR, and in this case, I think it's automatic recloser, not augmented reality. So one-phase tripping and auto recloser. And you want to also use 3 IO circuit breaker failure. This is not automatically blocked during one-phase auto reclose when you have only one-phase circuit breaker failure start active. And we don't find also possibility to block 3 IO circuit breaker failure when only one phase start is active. We would like to have 3 IO circuit breaker failure active only when there is a 3-phase trip and start active. Do you see any solution for that? And to this rather long, and for me it's a complicated question.
To be honest, not yet.
Not yet. So yeah,
I have to think a little bit more.
That's what I feared.
I have to discuss with the development, and to be honest, I don't completely understand it at the moment.
Cool.
But I know a little bit the problem here with the 3 IO. We have this special criteria when only the zero sequence will trip, and any combination with the 3-phase trip. But that's too much in details to give answers after 3 hours making presentation. Sorry.
I think so. Yeah, we will take that later. But I think I've seen that somehow the question was also displayed to the auditorium. If that's a nice new feature, we will learn on that later on. And I think we already talked about this 4000 hertz you just mentioned, and I see one question mentioning that again, because the question from VB is around what is the behavior of the 7SS85CU busbar protection in case the merging unit sends an SMV stream of 4000 hertz and 2 ASDUs, 4 times I and 4 times U. Is such type of the SMV stream kind of allowed to be used for the CProtect 5 7SS85? Long and complicated question.
So of our 7SS85CU solution, there's only sample value stream is 4000 Hertz in one ASDU and not included any voltages. So here we only transmit the currents to the central unit, but it is, if you use the IEC 61850 compliant solution, it is also possible to include a voltage stream, I would say. Do you have something to add?
Yes, but you answered it more or less correct. It will be not, we are using exclusively the 4000 Hertz 1 ASDU, and according to engineering, it will be only possible to bring current information into the stream. That will simply, it's a fully compliant stream, but it will simply not possible according to engineering workflow to add voltages. But you can, without additional cost or without an additional Ethernet module, you can also add a normal string, a flexible string. You can here an additional full compliant stream, which has not this automated engineering stream. And there you can do whatever you want. You can also use 4000 Hertz 2 ASDU, and you can also add voltage information. That's possible. That's no problem. But not in our 7SS85CU merging unit stream, as we have explained. And maybe I can also remember why we not recommend to use this 2 ASDUs for busbar protection, because if then one telegram is lost, we will lose immediately 2 succeeding samples, and this will lead to a blocking of the busbar protection if one telegram is lost. And therefore, we decided to use only one ASDU with only one sample.
Mm-hmm. Thanks for the clarification. And I think the question I will read now from AA is to a former part of the presentation: can these flags or internal calculations be exported to a ComTrade file?
Flags, internal calculations.
And I think it was about in the middle of the presentation, so...
The modified stabilization current, something like that? If this is part of the ComTrade?
The modified stabilization current, it's not necessary to export it. You will see every time in the ComTrade file, in the fault record, you will not see the calculated stabilization current. You will every time see the modified stabilization current multiplied already with the stabilization factor. I guess we will just for sure when next time when we go a little bit, maybe this part was very theoretical, and in the next part, centralized and communication, it will a little bit more practical, showing the engineering, going online with digital twin and so on. And then we will see also fault records, and you will see that this internal calculations are already visible in the fault record and in the ComTrade files.
All right. I have no idea if you can hear that. We have some constructions around us, and I'm really glad that we were through the presentation itself. We'll take one last question before you cannot hear us anymore. And the question comes from RA. In the circuit breaker failure and the end-fault protection, will that be an option during the ordering stage, or will it be a default function within the busbar protection?
Both functions cost some function points. So if you order a device with a pre-default set of function points, you have to make sure that these are enough of them. Or you use our function point manager, then of course there should also be these function points available. And for the circuit breaker failure protection, maybe we can repeat this here. The inherent circuit breaker failure protection costs no additional function point, and it's only the breaker failure protection for the external trips that costs additional function points.
And they deliver addition function. So
Oh, sure.
you get
They are worth the money.
Yes, I think so. So I think I have to admit there are some more questions, but they read so complicated that it will be easier to answer them in a written format. I guess that your heads are a bit filled. Ours here are kind of emptied. So that would be a nice mixture. I hope that you found the content of today's tutorial around the busbar protection functions, algorithms, and settings really useful and really helpful. And as I already mentioned, yes, you will get access to the recording, you will get access to the presentation, and you will get access to all the questions and the answers we delivered. And so I hope that we will meet you in our next tutorial session. Nina and Rainer will show the centralized CProtec 7SS85 and the CT dimensioning. So looking forward to meet you there. Stay safe, keep your assets protected, and see you in a few weeks. Goodbye for now.
Goodbye.
Bye.